I would like to thank especially Orca Computing for bringing our keynote speaker, Rossy and Nguyen, who is going to introduce the keynote speech. I would like to thank to IBM and Voica somewhere there in the back. Hi, our keynote speaker from last year actually, for coming physically to the event. I'd like to thank Capgemini and Marek Kowalik is also somewhere here.
Is here, yeah.
Hello. Marek Lewandowski is here, and Marek Kowalik is coming. He's in the back. Yeah. Hi, Marek. Hi, Marek. He also is from outside of Poznań and had to do the travel to come here and to be here with you. And we also have people online from Switzerland, from ID Quantique, who are going to support you. So we are lucky to have all those mentors, and there is 19 mentors that you can talk to, and please don't hesitate to talk to them, because we all know that quantum computing is a difficult area and it takes a lot of effort, a lot of learning that is going to happen today and tomorrow. You have the mentors, you have quantum computers. Quantum computer is the market price of quantum computer is around $1.2 per second. So you are going to get this for free. And so also don't hesitate to use quantum computers. I know not all of you know how to use it, not all of you are going to use it. You can be imaginative, you can be creative about how to use it. Why are we going to use quantum computer at all, and why are we meeting here? 4 years ago, from this stage, I was telling that there is almost 1 million people having cancer in Poland, almost 1 million people 4 years ago. This year, there is more than 1 million people having cancer in Poland. So our dream and what we would like to achieve is to meet in next year or in 3 years and say, hey, we have again less than 1 million people and the number is not rising, it's on the decline, thanks to using the quantum computer. It is possible. I strongly believe in this. It is possible. I strongly believe that you can contribute to such a goal. And this is just one example of what you are going to be challenged with today. Today you are going to meet 5 challenges, among those genetic analysis that is going to personalize therapies on oncology. You are going to take quantum computer and think, hey, what can we do with this machine, with this amazing technology that the world doesn't know? Is it actually as efficient and as good as the scientists tell us? So you are going to see and think, is it useful for me, for myself, for my family? Am I going to be proud of what I'm contributing here? So this is actually the challenge, the common goal, to use the quantum computer, to use mentors for your own sake, for your own benefit, so that you can, in 1, 2, or 3 years, say, yeah, I was actually part of this whole quantum revolution, from going from typing machine to the computer. Now we are going from classical computer to quantum computers. So this is a kind of a revolution. You can be part of it. By coming here, you are saying, yeah, I want to be part of it. So now the floor is yours. Please be creative and do the most of the time that you have been given. And also, don't forget the people behind it. There is almost 20 people going around these rooms. So if you need anything, apart from mentors, you can find mentors on the Cool Future website. There are people in shirts like this. You can ask them anything, and they will help you. So yeah, let's follow the better future together. The first speech will be delivered by Rossy and Nguyen from Orca Computing. Okay. Give her a loud applause.
Thank you so much, everyone. Hi, everyone. Good morning, and I hope you are, having a great start. My name is Rossy. I need to check if this one things work for us. It does. So my name is Rossy Nguyen, and I'm a head of product at Orca Quantum Computing. So it is an honor for me to be here because I should stay here. It's an honor for me to be here, but at the same time, very emotional and personal. so it doesn't work anymore. Back when I was a data scientist, I joined a lot of hackathon, right? Sometimes too many, sometimes two at once. That was a bit intense.
Raz, raz. Paweł, poprosimy o drugi mikrofon. Zamiast tego, raz, dwa, trzy, 1, 2, 3. Here we go. Sorry.
Nice. All right, we're back online. So what event without technical issue, right? So where were I? Oh, I was at the fact that I am still a hacker. So I joined a lot of hackathons. I love this event because this is kind of unique event, right? Because you have a very limited time. You're here together, you work on a sprint, and you explore new technologies. And for that, I think, I hope that you make the most out of today, because you also not only have the ability to run your code on the actual machine, but you also have a mentor around to help you with that. So one of my last hackathon was actually a quantum machine learning hackathon. It was organized by IBM colleagues here, and it was the Qiskit European Hackathon. It was like 3 or 4 years ago. It was still an early day where IBM just released their 20-qubit machine. It is, I think it's called Penguin. And the user of that hackathon had a chance, if they, to develop algorithm for this machine, but also have chance to run their algorithm on this machine as well. But at that time, it was, still early day of quantum computing. It was the day that the machine was located remotely, and you can only send your code virtually. Fast forward 3 years, we are here together in this hackathon, and you have the possibility provided by PSNC to run your code on actual machine that located in Poznan. And to some of you, it's your hometown. I know it sound incredible. For me, it is, because imagine this technology now in your hometown. This is the technological progress that we are witnessing. So I hope that you can make the most out of it. So in my talk, I will talk a bit about the system that Orca computers that you will be using today, but at the same time, how it can help you in your challenge. I'll try not to dive too deep into the exciting technical detail, because during the hackathon, you will have a chance to talk to us, me and William and Oma. We're all from Orca Computing, and we can tell you a lot of fascinating things about the machine that we built. So quantum computers is the excellent resource at computing and operating, exploring the property of quantum system. But there's not only one way of building this system. There's actually many ways, and there's not yet a winning way of building this system. So you have atomic qubit system, which use, for instance, trap neutral atoms and manipulating the qubits using laser beams. You also have superconducting system, like IBM system. This is actually based on superconducting circuits and use electromagnetic pulses to manipulate the qubit informations. Photonic qubit, on the other hand, is based on the quantum property of light, of polarizations and phases. This qubit is manipulated using an optical component called beam splitter, phase shifter, or detector. These are the components you will get familiar with more during the hackathon, because this is the one way that you can understand what contribute to the advantage of this system. So in Orca system use photon as quantum processing unit. As the fact that photon is a particle of light, it is quite easy to produce and manipulate. We also can use the standard optical fiber to transport this quantum information system. And therefore, we can actually leverage what is already existing today, vast telecommunication network. Quantum photonic systems also operate at the cryogenic temperatures. So whereas some other platform require very cold, photonic system operate at the room temperatures, whereas others technology required cryogenic temperature which close to absolute zero, which is around like minus 273 degrees Celsius, which is like 310 degrees colder than today. It's very cold, right? So, but the system that you will work with today is our Orca PT1 system. PT stands for Photonic Quantum Tambin, and it is the boson sampling device. So bosons come from the fact that photon is belong to one of the class of subatomic particle class called boson, as compared to fermions, such like electrons. So because photons is, a particle of light, it is, as I said, it's quite easy to produce, but at the same time, I think photonic system can be used in building the modular and fiber connected architectures. So if you think of universal quantum computer as general purpose machine, then this boson sampling machine is designed to be excel at one task, specific task. It's sampling. So this machine does sampling. It's quite simple, right? There's a lot of things like classically you can also do sampling. But the devil is in the detail. Sampling is actually a limitation of a lot of statistical models and machine learning algorithms. Boson sampler machine device can sample from the distribution that cannot otherwise possible classically. So this boson sampling can also, as I said, operate through room temperatures, but it can also help you unlock a lot of limitations in machine learning. So application from this system is actually a very interesting area because it spans across industry and across use cases. So as you can see here, there's some of the examples that at Orca, together with our partner, we together developed application for this machine. One of those can be, let's think of renewable energy, right? So if you're familiar with the topic, you know that most of renewable energy generation is a stochastic process, right? So in order to efficiently forecasting this stochastic process is require a lot of computations. And this is one of the use case that PT1, boson samplers, can really improve the forecasting ability of this algorithm. On another case, for instance, in satellite image processing, satellite image is taken from the sky. So most of the time, there's obstacle in between, like clouds, birds, you can name it. So in order to use this image efficiently, algorithm is required to, let's say, denoise the image, meaning that remove the obstacle, but also keep the image, intact. So generative algorithm was used, implemented on PT system to really improve the denoisation of these images. Right, completely different industry, same technique and same machine. Or even in biofuel discovery, where molecular structures, folding problems was explored, where algorithm was used to establish the position and the angle of the bonds between molecular structures. And the same machine was used to enhance the predictability. So as you can see by now, I hope that you can see that there's a variety of range of applications and problem you can try to explore and solve with this machine. But for the hackathon today, we invited you to tackle a challenge which we find can be effectively implemented using this technology. And that is biological image generations. So I introduce you to this challenge of fluorescence microscopic image. This is something I just so recently learned. And fluorescent microscopy is a very powerful technique that allows researchers to study the structure of cells in great details, right? And how this technique works is it works by labeling the molecular structure using fluorescent dyes or protein. These dyes emit light when a light source is excited through the light source. So what does that mean is that this whole process, you can imagine, is very costly and time-consuming. So acquiring data set is indeed, not the easy things. So in this case, we can use the help of machine learning and statistical model to really help to generate a biologically plausible new image. So what does that mean? It's not only fake image, right? The algorithm needs to learn the pattern of the real image and produce biologically possible and plausible image. And in order to do so, we advise you to use an algorithm called Generative Adversarial Network, or shortened for GANs. So if some of you don't know about this is also one of my favorite algorithms. So in a nutshell, what it contains two neural networks, that one called generator, the other one called discriminator, and they compete against each other, right? And they do this over time. So the generator would try to generate image that close to the real data, and the discriminator or the critics, you will see in the code called critics, were trying to distinguish between the fake and the real image. Because they do it over and over time, they were getting really good. However, during the process of the generator, I think the generator is a cooler one, because the job of generator is really hard, is how do you come up with the realistic image? So along the latent space of the generator, it's constantly translating the information from latent space into data. And then that data needs to resemble the real image. And for that, the latent space has significant impact on the trainability of the model itself. So in this challenge, instead of using classically compute latent space, we would like you to use a hybrid approach, a quantum classical approach. So in this approach, instead of using classically computed latent space, you will use PT1 to do this job, right? So you will create something called a quantum latent space. They will be more complex and hopefully will improve this algorithm. So don't worry if you don't get it right away. Throughout the hackathon, throughout this challenge, you were able to access our software development kit. We call it the Orca SDK. And in this software development kit, you will have tutorial, getting started with the machine. You also have material to learn about the machine, right? And this SDK also provide a programming interface to the actual device. And what it means is you can not only run it on the simulator, but you can easily port in your code and run it on the actual device. So, yeah. I think with this, I just wish you the best of luck and a fantastic time for today. Tomorrow is World Quantum Day, April 14, in case anyone haven't realized. I think this is a great idea from organizer to really pick the date of, how to celebrate World Quantum Day is not a better idea than to actually hack away a solution for this quantum system. So I would like to end my talk with a personal thought. So as I mentioned, I am a hackathon enthusiastic because not only this event is special, but I think it's really hard what you guys are gonna do. You're gonna come up with a solution for the problem you might never work on before. You're gonna work with the people you might also never met before. And you have 24 hours to get to the solutions. So when things get hard, persevere, right? Get to the end, understand what is the scope of the hackathon, what is the MVP, minimum viable product, and also enjoy the journey. Because in the end of the day, if throughout the event, what you're going to bring with you is the knowledge that you learn, memory that you share, and the connection that you make. So thank you, everyone. Yeah, and I would like to introduce Voica from IBM, who will present to you the challenge from IBM.
Let's see how this works. Okay, it goes well. Okay, hi everyone. So I'm very happy to be back here. I am, as Rossy was saying, that I was here last year at the inauguration of the hackathon. So I'm very happy to be back, and it's more people, more exciting. The topics are actually even more current to what the problems we have today. Yes, I'm part of IBM Quantum. I'm not alone here. I'm together with my colleagues, Tomasz, who is going to come, also he's going to be part of the jury. Aziz is in the back. He's the technical support. He's part of IBM Quantum support team. Lena, if you were hopefully listening to the QSkit introduction, she was introducing the QSkit tutorial and explaining how to get started. I have some slides as well on that. So this is our team today, but of course we are more, and we are very happy to be partnering with PSNC because we really love the partnership, because PSNC is really cool team because they are doing so many interesting and really problems, addressing problems that are really important to advance the technology. So with that, let me get a motivation as well. So I have a bit of explaining why we are so excited about quantum. Of course, you might already heard this many times, but it's basically because it applies the principle of quantum mechanics. So this is something super exciting because from the classical bits of 0 or 1, now we are having much more information that we can encode in a bit. And that's why we call it quantum bit. We are expecting computational advantages in certain areas. So this is something very important for you to also think. Though we are building universal quantum computers, that means that in principle we could actually address all the problems with the quantum computers, but the challenge is where it's actually more efficient, more effective than the classical compute, because we're having quite some advancement also with the CPU and GPU, and you see with the ChatGPT and so on, AI, so it's advancing very aggressively as well. So now we need to identify problems that are actually still not capable to be addressed with the classical compute, and that's where the quantum compute is coming very handy, because it's complementary way to look at the problems. So that's why not all the problems are efficiently solved by quantum computer, because it's too much overhead. So that's why you need to understand, is it worth it to actually put it on the quantum computer or not? So this is the picture basically showing that we have problems that can be easily addressed today with the classical CPU and GPUs, but when the scale of the problem increases with adding additional parameters, that's where the quantum computer could actually be more efficient. So this is the motivation behind why we are so excited about this new technology. And why for enterprise? Well, we are looking for quantum advantage. Quantum advantage can take in multiple forms. One is the speed, that you get to the solution faster. Second is you get more accurate solution with the quantum compute, and it may be cost efficient. So these are what we call quantum advantage. If you look at it, they're actually, in terms of methods, we are identifying basically 3 main methods that are at the current, with the current machines, are showing potential to outperform the classical compute. These are the simulating nature, because nature is quantum in itself. The mathematics and processing data with more complex structure. Imagine that you have matrices, more elements you add to the matrix to do matrix multiplication actually becomes more challenging with the classical compute. So this is kind of easy example. When you add additional parameter, it's actually increasing the complexity of the solution much more. And the search and optimization. This is more empirical at this stage. There are specific problems that you need to look in order to understand what is actually challenging in terms of from the point of view of finding the problem. And these 3 methods can be applied to different industry problems. So that's why you should think that, okay, there are actually 3 fundamental methods that can be applied to multiple use cases. Here is just categorization in terms of aerospace, automotive, financial, high-tech, energy, environment, and healthcare and life sciences. But there are multiple use cases that can be applied to different methods. No? So you can think about classification problems, that's machine learning, versus logistic, finding the solution with optimization problems. So this is just an example. Of course, today we are focusing on this part, on the healthcare life science. Some also motivation why industries are also very interested into it, because it's a potential to create money, to create market at the tech maturity, and this is shown in these three different methodologies: simulating nature, data with structure, optimization, and others. This is from the Boston Consulting Group study, and only by adding the minimum gain in the market, you get to $500 billion. If you look at the simulating of the nature, pharma and chemistry is on the first place. If you look at data with the structure, high-tech optimization problems, optimization under logistics. So this is kind of where the interest is as well in the world. So there is a lot of potential to actually unlock better solutions that bring to more value. Now, that's the motivation. But where are we with the quantum technology? And I'm IBM Quantum, so I'm an IBM-centric point of view, so I'm looking to see how we are improving the technology, because there is a lot of buzz, so we need to also actually meet the expectation. So for your information, this is a very busy chart, but this is our development roadmap and innovation roadmap. So innovation is what we are doing actually in order to get to the end user. So first we innovate, and then we deliver to the end users. So each column is an year that we are actually having a milestone that what we want to deliver. And we started with this roadmap from 2021 to show what we want to do. There are green check boxes, but shows that we are actually executing on our promises. The black rows are on the hardware stack. So we are also looking end-to-end solutions, not just the hardware. We want to make sure that actually the speed is done from the end-to-end, from the sending the job to actually being executed and the result coming back to you. So where are we today? So this is 2024. We have now quantum computers with 100 plus qubits. But it's not only the number of counts, it's actually what you can do with this, quality of it. That's why we are looking at to see how many operations you can do with this number of qubits, because that's what is also relevant, not just that you have a number of counts there. So we are at 127, 133 qubits nowadays, and you today can access them, and that's going to be something very scarce resource. So you are really looking at the best quantum computers, and I can say that because I'm IBM. So you are actually having access to the best quantum computer, the most performant quantum computer, but they are still noisy. So they are not fault-tolerant quantum computers. So that's why extracting performance from them is also a challenge. But today you just experiment also to think. It's a different mindset to think how to map a problem into a quantum computer. This is actually the main challenge, because you have to get out of your classical mindset to actually start thinking how I'm going to take the classical data and actually transform it in the quantum circuit. So this is a challenge of today. And I don't want to spend more time on this, but this is basically to give you reassurance that we are working on the quantum system. We are planning by 2028, 2029 to have the first error-corrected quantum computer. So these are important milestones. So it's happening fast. We are evolving very fast, and that's why security, it's becoming a threat, because with the quantum computer performant at the million of circuits and that you can execute, it can break the cryptography of today. So that's why it poses a risk of what do we do for that. And healthcare cares a lot about the data. So that's why it's a very matching topic for today. So what, I mean, I'm not going to go into details, but what does it make a performant quantum system is basically to have availability, reliability, and stability. As I mentioned, to have hardware, it's not enough. You also need to have a software stack. We are proposing QSkit. It's an open source SDK, open to the community, developed by the community as well. We think it's around 70% of preferred languages for the user because it's open source, because it's developed by the community. It comes with a circuit toolkit, an operator toolkit. You need to transpile from the logical qubit into the hardware qubit, and then you need to communicate through the primitives. So this is a toolkit that Lena has explained how to get started with it. So if not, the slides are available on Discord. But then you also need to get that propagated to the hardware, and that's for that we are having QSKIT runtime. So what it happens from the circuit, you need to work with the error suppression, runtime compilation, error mitigation. So maybe not today, but just for you to be aware that there is still more work from the concept to actually make it extra performance from the hardware, just to be aware of that. So here we are at the healthcare use cases where quantum can play a key role. As I mentioned, not all the problems are going to be solved by the quantum computer. So here is just some examples where we think that quantum computer can help complement the current bottlenecks with the classical compute. So it's not manual bottleneck. Classical computers were actually being done because we have a lot of problems which are also because they are not digitized. But quantum computer will not help if the problem is not digitized. So that's why you need to also think of the reality where we are today. So the three problems that we think are relevant for quantum computer, and not only, are the precision medicine, where we want to keep people based on the maybe specialized treatment just for the person who has the problem, rather than just apply general solution on you. Diagnostic assistance, so better diagnostics, because as you know, I mean, Adam was mentioning the cancer, and cancer also is one of the reasons where to detect the cells that are actually cancerous, and sometimes it's because the machine learning classifying is not doing proper job. So that's now an interesting problem to actually address. And we have lots of research institutes looking at that. And insurance pricing optimization for different problems. So this is, on one hand, one of the main problems that it's being worked right now. Nevertheless, what we are proposing for you to get started with, to think about, is the public health optimization. As you know, actually even to schedule an appointment is not really trivial, and we are proposing to take a look to see what are the challenges to identify problems in public health care. So we give you a lot of space to actually identify problems that make sense to take a look with it with the eye from the quantum computer point of view. So what we will be assessed on the technical part, innovative way to leverage quantum computers. We hope that you're going to be using quantum computers, but you could start with the simulators as well, so just to think about of the idea. The clarity and simplicity of the description, elegance of the QSKIT code implementation, solution implemented end-to-end would be great. And what is important is to scale, because now we have these few qubits, 100 qubits, but how do you actually scale this problem? Is it a problem that can be scaled? So you also think about mathematical calculation a bit on them. For the concept presentation in a form ready, I mean, it's an elevator pitch. We also need funding to get actually projects approved. So you have to think, if you're going in that direction, to think how to actually put in the position that you want your project to get money to be funded. So this is something we really appreciate if you can come with a very practical and pragmatic approach to it. And innovative way to leverage quantum computing specific. We are providing some supporting material, so you can think, here it's not limited to, restricted to. We think the open data from the Kaggle would make sense to take a look already what is being actually digitized in terms of data when you do an appointment. So for example, you have a patient ID, you have a gender, appointment date, age, and some specification, and you could think, are these features helping? What features do you need to get your problems? There are some examples, because as I mentioned, if you were paying attention, the quantum computer basically has three methods. These three methods can apply to different use cases. So you don't need to only look for the use cases that are healthcare, because the idea is actually to come with methods that maybe are applicable to other industry, but you can apply it to the healthcare. So synergy between different concepts are also very important. And that's why I'm giving you some example here. For example, ExxonMobil is looking at optimizing the route for the shipment of the containers that basically, and it's a scheduling problem as well. So that's why take a look to see how they are resolving it. They are using the variational quantum eigensolver. This is for the optimization problems, but the principle behind it is similar. And I don't want to give you too many details because I want you to go and explore, because you need to come with a fresh mind and think about what could be applicable into quantum computer. Another example is, again, vehicle routing by Hyundai, making scheduling optimization. I have a bit more on that, so get inspired, because, for example, their problem was given locations, charging stations, fleet of electric delivery trucks, the truck schedule, they had to minimize the distance, time, and number of trucks being sent. So this is very practical problem. You can even see with the traffic, with the trucks. So this is something, take a look to see how they were being addressed. So, and we've seen there that the problem size increases the more parameters you add, constraint you add to your problem. So the location, the number of location, number of variables, and at certain point, more than 200 location, it becomes really, really challenging to be addressed with the classical compute. So what they did, they basically started to take a look at the small qubit problems, 10 qubit, 55 qubit, and 75 qubit, and they're already collecting actually, what was encouraging that they were using the sampling-based variational algorithm to show that they can use it on the hardware already, this kind of problems to solve it. So this is why I'm saying that it's very good potential to actually apply the same tools into healthcare scheduling problem. So how do you get started? As we mentioned, it's easy. So you just need to create freely an ID on IBM Quantum System, and then you get access to our platform. Through our platform, you can actually have, so I have much more here. So you create, this is a slide how to create an IBM ID. This is how IBM Quantum Platform has. Important is that you get a page, but this is API token. That's the one you're going to be using in actually to accessing the quantum computers, but you don't need to immediately run on the quantum computers. You can actually get a bit of learning. We have courses, we have tutorials, and what is QoA and what is VQE. So these are the algorithms that are being used for the optimization problems. So take a look into that. You don't need to start from scratch, right? So this is, you don't have time. It's very, in 24 hours you need to come with a solution. And you could also get maybe more intuition with the platform, looking at the composer if you want to understand how to actually use the quantum mechanics behind the superposition and entanglement. What does it mean in terms of results? So this is a bit maybe of the playground to understand how to code. We have more example on how to use variation algorithm on that platform, and how do you actually, you don't need, you could use your laptops, but you could also use directly the notebooks. You have maybe different tools, but IBM Quantum also provides access to the lab, where you can actually don't need to worry about how to install Qiskit and do all the libraries being considered. So it's everything contained in there. And once you create a notebook, you have it stored in here, just for awareness. And as you will have access through the open plan to the best quantum computers, so the 100 plus qubit systems are gonna be there. But warning, you have 10 minutes free per month per user. So that's why you need to be smart, not to spend your 10 minutes just because you tried. So you think about the problem, try to see, make sure that there are no code errors, and send it. So the 10 minutes, I mean, it's quantum compute. It's really time on the hardware, not the classical part of it. So just to be aware. It still you can do something, but just to be aware. And with that, you can explore more. And I'm done with that. So yes, enjoy. And I need to pass to the next challenge. Who is the next challenge?
So the next challenge is coming from Capgemini. And thank you very much. Thank you, Voica, for presenting your challenge, and also for bringing to us 3 other members of IBM team. That's great to have Aziz, to have also Lena and Tomasz Stopa. Thanks for coming all the way from France, and thanks Rossy for coming all the way from France also. Oh, I thought Switzerland, but yeah, or UK? From the UK. So you came from the UK. Outside, maybe not Europe, but outside the EU. Yes. Yeah. So it seems a bit further because of that. Yeah. And now we have the fantastic team of Capgemini, 2 Mareks. So it's easy to remember. It's Marek and Marek. It's just Marek Lewandowski, with whom we do a lot of other stuff as well, apart from hackathons, and Marek Kowalik, the expert of Capgemini in quantum computers. The floor is yours.
Thanks, Adam. So it's going to take just a few seconds from my side. So I will say a few words about Capgemini, what we are doing, what is our company focusing on, and then I will leave a stage to the other Marek, who will introduce you to our challenge that we have prepared. So Capgemini is a global company that was established in France. So we are a French company with right now more than 350,000 employees all over the world. And the company is more than 50 years old. So we are very, let's say, a seasoned partner for our business partners that are from various industries. What we do is we collaborate and we cooperate with the biggest companies all over the world. So we are a partner for the most remarkable brands and companies from industry, from medicine, from transport, from logistics, from automotive industries, and also from the financial sector. So I'm pretty sure that whatever brand you think, world famous brand you have in mind, we are cooperating with those people. And in Poland, Capgemini is also a very well established, so we've got offices in various cities in Poland. Locally, if you are from Poznań, you can think about us as a software solution center. So we are shaping and we are tailoring software products for our for the companies we are working with. But we also are doing a lot of work from the industry, from the engineering perspective, and also we are cooperating with our partners from IBM and IBM Quantum Computing Lab, which Marek will say you a bit more about it. We are a very big company from the local perspective, so you can see here is more than 10,000 people plus working right now in Poland, and we are in fact a global delivery centers for our partners all over the world. We are a huge company. If you would like to say hear about a few words about our projects, about our partners, don't hesitate to reach me. I will be here today and tomorrow. Just grab me and I will tell you a bit more about our company. And now I'm leaving the floor to Marek, who will continue with the quantum topics. Thank you.
Yeah, thank you, Marek. Yeah, so I will try to manage the time. First to tell you about the Quantum Lab and then about the challenge. Yeah, so basically Capgemini Quantum Lab is per se the Global Innovation Lab, which collects the experts around the Capgemini to work on the quantum technologies. Our mission is 4 words, so basically accelerate applied quantum advantage. When it comes to each word, yeah, basically quantum is self-explanatory. For the accelerate, it means speed things up, not necessarily wait for the real quantum computers to achieve level required by particular use case to be somehow advantage applied. Yeah, focusing on use case, research on use cases, on the adding business value. And then, of course, advantage, so in some way better than classical or hybrid version. So, yeah, self-explanatory. Okay, when it comes to how do we build this mission, we require, or we are trying to go within 4 directions. So first one is strong domain experience, which is crucial because not only quantum expertise, which is our second direction, is important. Now quantum technology, adding the business value, will happen in a vacuum. We need collaboration with the domain experts, with people knowing the use cases, the how it's done currently, to point out the places where there are bottlenecks when we can, suggest something out of the quantum perspective. Flexibility through collaboration, like any industry, any company have slightly different culture. A lot of time before coming out, even with simple feasibility study or working together, it's just worth to meet each other, know how things are working in the company, how they are working on new technologies, and basically show something, see if we can something in common, and then proceed seeking the place for applying quantum. And of course, ability to scale, because for now the projects showing the quantum advantage are mainly feasibility study or comparison of complexities or just benchmarking on a simulators. But when the quantum computers are growing in quality and so on, and we can think about larger scale problems, we need those capacity to fulfill the scale to actually implement commercial technologies. Okay, to speed things up a little bit, Quantum Lab is working on 3 areas, all 3 areas of quantum technology, so quantum computing, quantum sensing, and quantum communication, which quantum communication is particularly important to break it down. This is quantum and post-quantum cryptography. So first one is quantum communication, as it is, and another one is working on the classical cryptography protocols, which are unbreakable by the quantum computers. So let's keep up. When it comes to our work, primarily internal research in terms of the number of projects, but also collaborations with other companies for the feasibility study. With our portfolio of realized and current projects, we are trying to fulfill most of the areas to being a quantum stop shop for all. I won't brag about all of the projects. It's just important that, for example, in quantum computing, you need to take a look in sort of 2-dimensional way. First one are the use cases as they are, and another are the areas of the quantum computing. So, for example, you've got for quantum computing, to name a few, you've got quantum simulation, quantum Monte Carlo, quantum chemistry modeling, or maybe quantum optimization. And across those, you've got the use cases. So you've got use cases from the financial services and so on and so forth. So this is how we look at this and trying to fulfill those. Okay, to throw some specifics, just one thing. This is our framework for the quantum chemistry modeling, which takes into consideration current quantum devices to trying to operate on low number of qubits and also shallow circuit depths. And this is quantum-centric, data-driven R&D, which is terrible shortcut, which is QDD R&D, and even British people from Quantum Lab struggle with it. What's going on with this? Basically, we are taking the molecule or the material, taking some quantum chemistry aspect of it, which can be, for example, electronic structure. Just take a piece of fragment which is interesting for us. For example, for covalent drugs, you may be interested in the reactivity. And reactivity, when you are developing some drug which should finally go to clinics and be used by people, have very narrow window of the reactivity, because you don't want to have too many side effects or any of those, but you also want to have your drug to be efficient. So basically, just focusing on the reactivity tells us, okay, there is certain fragment, which is sulfonide fluoride group, particularly for the covalent drugs, which depends, which the reactivity depends. So basically we embed only this fragment, transform it on a quantum computer, run it on quantum computers, and get some value which describes this fragment, which we are calling quantum fingerprint, which is used as an input to predict the reactivity. So this is good information because we don't need like exact value, for example, exact energy, something like this, to use as an input to some, let's say, machine learning model to predict the reactivity. So that means we can put into work, current quantum computers. This project on the covalent drugs was performed with the GSK. Right now we are using on the very similar project within same framework for the biodegradability of the esters. One aspect is, of course, the environmental things, how esters are degrading, but another is the shelf life. So basically to predict how much the esters are in their shape, where they are providing for the cosmetics, their aroma and so on. And this one, right now I don't have it on a slide, but we are doing this with collaboration with Unilever. Of course, this framework can be extendable to other drug discovery and other material sciences as you want to. Okay, 10 minutes. Let's wrap up the challenge. Can I please the presentation? Okay. Now a suspense builds, so we need to wait a few seconds. Okay, we are ready to go. So right now we are here on the QL Future Hackathon. And this edition is about health and safety. So what we've got for you is the working on the genetic analysis. And the algorithm or the area which we want you to focus on is the genome sequencing and comparison. So basically DNA can be written down as the sequence of letters, and basically comparison of those is the bottleneck of the genome analysis because of the length of it. You can use quantum computing to optimize that. So basically that's our challenge in one word. But of course we need to add some context to that, more broader than just comparing the sentences of DNA, to put into business context the genomic analysis as it is. Let's first break it down to 4 areas, how it looks like, and then some applications to point it out, to motivate it. First one is genotyping, so basically taking 2 genotypes, taking 2 DNA, RNA sequences and compare it. And you can use it, for example, to take a look to viruses and just take a look if they are the same variation or they are different variants. So this is one example. Another is gene expression analysis. This is how some genetic predispositions are realizing in your, as a human or bacteria or any other organism, physical features. So basically you may have some predispositions, but it's not necessary that it will express. And basically this area checks this and also examine what are the environment or other influences which determine if some feature encoded in gene will express itself. Epigenetics, so this is slightly other direction. So this is checking what defines different outcomes of particular genes. So basically what's going on in a cell, on a cell level, on the DNA level, that we've got the same sequence, but the features expressed are changing. So you can imagine, for example, the cancer mutations. You've got the same DNA, but some cells are prone and are making its change into the cancer cells, and some are not. So this is this area. And of course, finally, CRISPR, genome editing. So really diving into DNA and changing this. There is a lot of areas and applications of it which I wasn't aware of, and it was a real pleasure reading about this to prepare this slide, to name a few which are like crazy. Of course, for example, for CRISPR genome editing, you can say, okay, we've got GMO, something like this. Probably you also know that some of the SARS-CoV-2 vaccines, so the virus dependent on the COVID-19, was one prepared that it's changing the DNA structure, which is exactly using the CRISPR technique. But to tell you some, maybe not that popular ones, would be, for example, for genotyping. You are using this for determining the genetic diseases or predisposition to diseases. But this is also the technique which is used for parenthood testing, so fatherhood and motherhood testing. Also molecular epidemiology, so identifying viruses and bacteria mutations. So this was, for example, used for checking the origins of the SARS-CoV-2 virus. Gene expression analysis. One particularly interesting use case for me is that you can personalize the treatment. So basically from the family of drugs which is useful for treating some particular disease, based on your genotype, you can take a look and use the proper version of the medicine which will have the best effect on you. Also, same comes with the chemotherapy. Some chemotherapies are working better depending on some predispositions, some genes you have. So that's it. And we don't have time to finish next two, so you can read it afterward. Some specifics to take a look. We've got genome, we've got DNA sequence, we've got human genome with 23, probably, chromosomes. And there are some diseases which are encoded in your genome, or they are not, if you are not having this disease. One of the genetic diseases is SCA, so single cell anemia. And the problem with it is that it's anemia, as it is, has many variations, but usually it's the effect of, for example, low iron diet, stress, like pregnancy. It's basically because of the environment, but some people has the variation of the HBP gene into their genotype, which makes them born with anemia. So basically, this information is encoded in particular place, in particular chromosome. So it's 11th chromosome, particularly fragment 11.5 probably, and you have one particular sequence, which we know that this is the mutated version of the HBP gene encoding the sickle cell anemia. How do we do it? Let's take a look at the basics. We are taking the DNA. We can encode this sequence into a series of letters by taking just one string of the DNA and respectively take the nucleotide pairs, first letters, as your encoding scheme. So for thymine, adenine, guanine, and cytosine, you are taking CTAGC. Yep. You're writing this into an array. It's encoding, it's the simplest one, first letters. And how do we check if some person is sick on a sickle cell anemia, or to be more precise, sickle cell disease? So we are taking the genome of particular person. We are taking the version of the gene, which is mutated one, which is dependent from the sickle cell anemia, and compare those two. If we can find a place when those two checks. So basically checking if this person in the genome has basically this version of the gene. No, and before the genome ends, we have find the fit. So basically this is how the algorithm looks like, quite simple. But there is a bunch of things along this which are not making this as much easy or help us make the algorithm more efficient. I will take a few seconds to tell about one technique which is used for this analysis and one which is used to optimize those algorithms. First one, DNA is a living structure. There is mutations, variations. We are not using one-to-one comparison because that's impossible to find anything. We are using something called Hamming distance. So basically, if for a sequence there is some percent of pairs which agrees, we are putting up a threshold. Okay, close enough, that's it, this fits. You can take a look at the definition below or more definition, just a few examples to understand it. So for example, DH for 4 sequence, for element sequence, if all of the letters are the same, it's 0. If 3 letters are different, it should be something came very wrong in these examples, but you get the idea. Hamming distance is as many characters are differing in 2 sentences. So yeah, we've got here fit. It turns out it's fitting, so we accept that. So this was about the what techniques are used for it. When it comes to the optimization, the sizes, both of human genome and the HBB gene variation, are that long that it's very inefficient to do it. So what we can do is we can take a very, very small sequence of the initial string of the gene variation, compare it, and we have potential fits. And out of these few potential fits, we can then perform the full-scale comparison. So this is one of the optimizations done classically. For the real business use case, we don't have time. You can go back to this presentation later because like identifying single cell anemia is made by the obvious things that people going through. So basically, if someone is ill, he will know it, and it's not required to have a genome analysis, which is also expensive. Okay, when it comes to the classical challenge, here you've got a bunch of numbers to compare it. SARS-CoV-2 genome contains around 10 to the power of 4 nucleotide pairs. For human genome, it's 3.2. So basically, when we have primitive comparison one-to-one all of the genomes of the 2 SARS-CoV-2 viruses, you will have around 10 to the power of 4, maybe 5 comparisons. For the human genome, suddenly it rises up to 10 to the power of 14. Then, yeah, we need to apply some tricks or optimizations, and it's still main bottleneck of the genome analysis. So, we have a challenge for you, which you can take a look. You can take a look at the quantum implementations, try to do it, see how it works, see if you get better scaling of it, and yeah, maybe overcome this bottleneck of the genome analysis with quantum computing and unlock new potential applications. Okay, we are run out of time, and I want to say a word about the data set. Can I get 5 additional minutes? Okay, I got the agreement, nice. Okay, so sickle cell anemia is not a good use case to provide the business value because the symptoms of this anemia are visible. If someone is ill, he will know it usually in early years of its life. So basically, anemia in general may be caused from a variety of reasons, not only SCA. And disclaimer, I'm not I have no certificate about the medication, about anything like this. This is just perspective of the computational scientist, nothing else. So, if I had it after it, the anemia may be caused by a variety of reasons, like huge loss of the blood, which can happen during the operations, during some car crashes, for example, but also chronic stress, low iron diet, autoimmunological diseases, something like this. So basically, we have we may focus on the anemia with people without the SCA disease. Okay. It turns out that some people are more prone to be ill to anemia or for the anemia to occur than some other people, even if they are not sick to the sickle cell disease. Basically, it turns out that in the quite high percentage of the risk group are people with TMPR SS6 gene, which basically depends on the some particular substance in our organism, matriptase-2, and basically this protein is suppressing iron regulatory hormone hepcidin. So basically, the problem is that someone can have the anemia coming from low iron levels in the organism because the protein which is suppressing taking down the iron is not working properly. And it turns out that this gene, we have map of it, we have some variation encoded, and we can take a look and take the genome of particular human and see if it has predispositions to the anemia, which is very important if, for example, we decide if to make a blood donation, or, for example, how many bloods to prepare if someone is basically, in the operating room. So currently, it's not possible to define at scale the predispositions to the anemia at operating rooms, at blood donation centers on a large scale, because it's expensive and it's inefficient. Okay, when it comes to our data set, you have 2 files, or 3, but I will, first let's start with 2. So first one is just this gene depending from the predisposition to anemia sequence. So this is full sequence of this gene. And another file is the human genome. And we have prepared 2 versions of this genome. So first one is a person which has anemia predispositions, and another one is healthy one. So basically, we didn't tell you which one is which. You can encode it on yourself. This is like mini task during the hackathon. But basically, those 2 are not that synthetic, because this human genome is a fragment from real human genome, and this is exactly fragment which is taken from the 22nd chromosome, where we know that this anemia predisposition is located if the person has the anemia predisposition. Here we've got also the data sources if you are curious after the hackathon to take a look and play on yourself or extend our data set. Okay, when it comes to challenge for the technical paths, try to implement gene sequencing comparison algorithm using quantum computers. You might require a bunch of optimizations and toy model testing on a smaller scale, because you need to get some feasible results on the simulators using like 5-10 qubits, not starting from 100. So you will probably need some optimizations on the classical side. But basically, check on yourself, implement if you can perform the gene sequencing using quantum computers. And basically, this is the technical part. For the concept path, you may create a vision about how the world would look like if we can have the genome analysis on a larger scale. So basically unlock the use cases which currently are rejected because of the scaling of the classical algorithms. Okay, 2 seconds left, made it. So basically, I will be 1-2 hours after finishing the opening ceremony to answer your questions. Also you have on a Discord the one-pager with the links to the exemplary algorithm to implement that. Thank you.
Marek, just before Marek's presentation, I asked him to, okay, super, Switzerland's all online. So I asked Marek to keep his challenge description simple. I hope he made it for you. If not, or if yes, he's available for you. Basically, for me, it looked like a strategy for science for Poland for the next 10 years. But you have only 1 day to do this. So please don't be afraid of that, because the jury knows that the challenges are exceeding the time and capacity that you have. And to make matters worse, you are going to have only 5 minutes to present your results. So the jury also knows that you have too little time to present it, and please bear in mind that you are not going to be able to present the whole of the work that you are going to do today and tomorrow. So also be assertive when thinking about your presentation from the start, right? So that you don't get frustrated that you're not presenting the full image of your work. It's not going to be possible. It's only 5 minutes. The next presentation is coming from Switzerland. It's online. It's ID Quantique. I was told we have the presenter online. Paweł, can you put up
Hello,
ID Quantique?
do you hear me?
Welcome.
Yes. Yeah, it's great to join you at least remotely. I'm Florian Fröwis from Quantique. We're happy that we're able to support your event, your hackathon this weekend. And I think it's part of this starting ceremony to increase a bit this suspense. So I'd like to take 2-3 minutes to also say a few words. First of all, I'd like to congratulate you, not only that you Okay. Is there any problem with the sound?
Okay,
Yes.
thank you.
Okay,
Thank you.
thank you.
Thank you. Thank you. So we're almost done. We're done. We're done. We're done. We're done. We're done. We're done.
There is an echo. There is echo. There is echo. There is
1, 2, 1, 2, 2, 1, 2, 2, 1, 2, 2, 1, 2, 2.
Can you hear me?
Yes.
Can you hear me? Can you speak,
Yes.
please?
Yes. Test 1, 2, 3. Test 1, 2, 3.
Please speak.
Test 1, 2, 3. Test 1, 2, 3. Test 1, 2, 3.
Right now. Can you speak something?
Yes. I'm speaking. Do you hear me?
Can you speak?
Yeah, I'm speaking.
Tak.
Yes.
Wait a second. We need to
Sing a song.
have some problems. So
1, 2, 1, 2, 1, 2, 3.
1, 2, 1, 2.
Okay.
1, 2, 3.
Yeah.
I don't know what's
stage.
happened here. So the next presenter will be Sophie,
So
and
as you can see,
you will
it's
speak
not,
after her. Okay, so
the
a few
remote
minutes, and
participant.
I will.
ID Quantique is preparing their presentation, and now we have Poznań Supercomputing and Networking Center, Sofiia. Welcome, Sofiia.
Hey.
She's presenting another challenge, which is
Medical AI assistant.
yeah. The floor is yours, please.
Thank you. Where is the controller? I have one.
Can you
Hi.
speak?
So,
Can you hear me?
AI medical assistant. To make diagnosis, there are two main issues. First, we have to deal with patients to make a diagnosis based on their symptoms. And the second, we have to classify the disease using some medical data. For example, image from MRI. But let's be honest, it's pretty expensive and time-consuming, isn't it? So to make it more available, faster, and much cheaper, data scientists try to develop, try to use such tools as recurrent neural networks or language models and neural networks for image classification to create medical AI assistants. But the problem is such tools has not high enough accuracy. In order to get this high enough accuracy, we deal with even more problems, which is limitation of computational power. It seemed to be obvious, just increase number of processors, right? But it's very, very expensive. So we literally spend hundreds of thousands of dollars to train ChatGPT every day. And even if we have enough money and computational power, we still training is very time-consuming because of huge number of parameters in neural networks, and it creates such a damage for environment. So we have a hope
that using quantum computers, we can solve all of those problems. We can try to increase speed of training, increase accuracy, and at the same time, decrease the amount of parameters. That's why PSNC wants to give you an ability to try the most crazy ideas and test them on real quantum devices. So your task is to create quantum or hybrid neural network for image classification or a language model or recurrent neural network. Here you can see an example of two data sets. First is for image classification, that is types of breast cancer. And the second is data set for language model. For a quick start, we created several tutorials how to create classical recurrent neural network or language model and how to create a neural network for image classification. So, to insert some quantum computing there, you should use such tools as Qiskit, Penny or Orca PT series. If you want to use real quantum device, you should deal with Qiskit or Orca PT series. For neural networks, you can use TensorFlow or PyTorch, but you can implement it from scratch, so you will have better understanding of concept of neural networks, and maybe you will find more efficient way how to insert quantum computing there. So, don't be afraid of any ideas. We are here to help you, and good luck.
My Meg, and I hear myself. Anyway, I'm going to introduce to you the last challenge that you will be able to pick and solve during today's and tomorrow's hackathon. But first, I will ask you a question. What do you do to prolong your lives? Do you maybe try to be healthier in some way? Do you eat more healthy food? Or maybe you quit smoking? Or maybe you try to reduce the amount of alcohol you consume? Or maybe you try to reduce the probability of having some accident, and you are very careful when crossing a street, or maybe you fear of traveling by airplane because you are scared of some terrorist attack, or maybe you do just the complete opposite and you travel only by airplanes because you believe this is the safest way of transportation. Well, let's have an example. Most people, including myself until very recently, believe that optimal blood pressure is 120 and 80, and this is true, but some people tend to believe that something a little bit above that value and something a little bit below that value is also okay, which is this implication is not true, because then people think that if they have something above that value, it is also okay, which is already false, because it's already considered high. Values are in the range of 90 and 60 up to 120 and 80. Why am I talking about that?
Ja bym na swoim laptopie to odpalił i jak pamiętam, jak z tego się...
To wpiszesz? Bo to
w sensie Stopa wywołyczną?
No. I want to tell you that other diseases are not important or something else, but statistically speaking, you have the highest chances of dying by heart diseases. And the problem is, the problem is that clustering heart diseases is an issue. And firstly, what is clustering? And secondly, why is it an issue? Clustering is basically a machine learning approach where we try to group together similar cases, similar patients, but at the same time we want to separate groups that are different from each other. And this is kind of machine learning approach that it is unsupervised. So we just have the data. We don't know what are the labels, but we still need to somehow distinguish the cases. And your task is basically,
can you hear us?
if you choose it, it would be to look at the data and try to apply quantum approaches in some way. It can be by dimensionality.
Do you hear me?
Maybe quantum computers can help you to reduce
Is it
number
good?
of attributes. That's how will make a clustering, or maybe you can try to find some quantum clustering algorithms. I know there are some, but maybe you can implement them. You can somehow extend them, somehow maybe combine with classical approaches. Or maybe there is a way also to use quantum computing to visualize the
Hi, sorry, can you say
outcome.
something? We just need to check whether it works.
That's
Me?
basically
Yes. Hello?
the task.
Do you hear me?
And good luck from me. Have fun.
Hello.
And that was all about the tasks. And I also
Yes,
wanted to
Everything works.
show you that
Thank
we
you for
have
that.
something
Now
similar
you
to
will be
what already Voica from
presented.
IBM said.
You will be
that you
presenting
can
in a couple of minutes. We'll tell you when to start. Sorry about that.
Jupyter.quantum.psnc.pl with a password quantum 2024. You have access to a website, a portal, where you have every tool that you could use. Every tool is already installed. So if you have any trouble with installing, I don't know, PT series library or Python or Qiskit, then you can use this website. You can launch Python kernel and try to code there. There are also some tutorials there from quantum for quantum algorithms, so you can check and see what's inside. Okay, so I guess it's now the time for quantum lottery. Are you, Mateusz, hosting this, or are you plugging?
Yeah, actually, we have a backup plan for ID Quantique's presentation, so
okay.
I will try to pin them in from my laptop. So,
thank you.
Thank you, Tomasz. Thank you, Sofiia. It was almost the final challenge presented. We are still looking forward to ID Quantique, who are going to present online. While we are waiting for them, I'd like to share with you that you are going to get workshops on your pitch. So workshops on how to present, etc. They're going to start at 12 today. And first, you will have them on the top floor and then on the first floor, which are the floors, other floors in this building. And Evelina, standing here, is going to run those workshops and tell you a little bit how you may like to prepare yourselves for the pitch, for the public speaking, and from the perspective of the jury and mentors that are going to judge your pitches tomorrow. Evelina, would you like to add something to that? There are going to be 2 workshops, right? 30 minutes each. Where are they taking place?
They're taking
You hear
place
me?
first at noon on the
I can't hear you.
floor. So those teams that be elected to have their work over there. So I strongly recommend to be on time, because thanks to this workshop, you'll find out our experience
You can
from
start.
previous hackathons.
Do you hear me?
What
Is it okay?
judges did
Okay.
look at.
So yeah,
their
after a few
experience to make
technical issues, I think we won't have these issues anymore once the quantum internet is fully established. So then there will be no problem anymore with.
Wait, sorry. We need
since
one more
you're gonna
second.
have
Yeah.
only this 5 minutes,
Okay.
it's really good to use our experience and to find out what to do to make it most effective. So first I'll be there on the 4th floor. After half an hour, I'm coming to the first floor. So those teams elected to be over there are invited to have this workshop at 12:30, and we'll have it for half an hour. I also asked one of the mentors to be with me over there, so you have like the first questions also related to the criteria you'll be evaluated by. They'll be there with me, one of them.
Great, thanks Evelina. And also Tomasz mentioned about mentors who can tell you about Qiskit. Please remember there is also Lina and Tomasz and Aziz from IBM who are also very knowledgeable about Qiskit. You can reach out to them as well about that. In the group of mentors, you also have judges. Judges are the most important. There are 6 judges, so please talk to them whenever you find them. Here's one judge, that's Chris. There is another judge, that's Marek, Capgemini. There are 6 judges. It's the best way to find out what they are expecting by just asking them. And they are here for you. They are not going to be there all the time, so please catch them as long as you can see them. There is another session with mentors and judges between 5 and 7 p.m. today. That's another opportunity to grab judges, to grab mentors. And you can reach out to them also via Discord. I strongly recommend to enter Discord and also to talk to mentors, judges via Discord. Are we ready with
I'll just
presentation?
Sorry about the technical connection. Can you actually say something to try the...
Yes, test, 1, 2,
it works. So yeah, the floor is yours.
Sorry about
Sorry.
Okay,
that's great.
great.
So
Yeah, I wanted to say that I think once quantum internet is established, we won't have any more this problem. Quantum internet will solve the WebEx challenges. Let's cross fingers. Okay, hello everybody. I think it's my job to keep you a few more minutes away from starting with your challenges. But I just wanted to say hello and also some greetings from our company, Quantique, who is also supporting this event. I think, I would like to congratulate you not only that you're here today at this event and take the challenges, but it's also congratulate to all of us to be at the right time to co-develop and help quantum technologies to become part of our society and to create value based on science that was done 100 years ago. But also congratulate you because you're in a great country. We observe obviously what's happening around the world, and Poland is really one of the hotspots. For example, in terms of key distribution, where we are active. We see a lot of interesting, very promising activities in Poznan, thanks to PSNC and others in your country. So it's really great to see. Also quantum computing. Sort of press release Orca, and yeah, it's really great, and I think we can be very happy about this. Maybe just to let you know about Quantique. So Quantique is a company, pure quantum company that was founded more than 20 years ago in Geneva. And we are working on photonics in general, which leads to different applications. So we have quantum random number generators, we develop key distribution, and we develop instruments for quantum optics labs, mainly single photon. So the core technology is detection of single photons and let's say processing of this. And this leads to various applications, as I just mentioned. I think this is the great thing about quantum technology. So there is some core technologies, photonics, atomic physics, superconducting physics, and they lead to a very broad range of applications. And interesting enough, things come together at different time. For example, quantum internet is one of our big goals, our long-term goals, and there what we do in the level of quantum key distribution, for example, will then be combined with other elements that are currently more focused on quantum computing. And for example, one of our main interests is SNSPD, superconducting nanowire single photon detectors. So these are best-in-class detectors. And from a physicist point of view, it's just amazing to see the developments, like how much can be done in such a short time. So these detectors are very sensitive. They have a very low jitter. They have a very low noise level, and we can now go to photon number resolution. And this brings kind of detectors to a position where it enables or supports quantum computing based on photonics. And so Orca is also working on this. In Poznan, and yes, so this is very exciting, and wish you very exciting weekends, a lot of fun with your peers, solving the challenges, and working on this, and contributing to make quantum technology a valuable technology for the whole society. So have fun, and see you next time in person. All the best. Bye.
Okay. Thanks for the talk. So you're of the big screen right now. And now, once the presentations are finished, I would like to present the quantum lottery. So thanks again for this.
Okay, bye. See you.
On the WebEx right now. And I would like to do the quantum lottery. So some of you probably already had teams when you came here. Some of you are still looking for a team. But right now we expect the teams to be forming or ready. And I will make a lottery in which I will assign teams to their tables. So the majority of the tables are on the last floor of the building, the fourth floor, and also on the first floor. But there are also some tables here in the basement. And the basement will also serve as a chill-out zone for everyone. All the stuff like the food, which is probably important for most of you, will be held here. And right now I will switch to. Could you please switch to my screen so I can just run the lottery, and I will just ask teams to just like say their names, who wants to be assigned to a table number, and I will just, using a Orca quantum computer, actually, a physical device, I will actually present their table number to them. The only thing, please just remember this number. And at the back there is a couple of girls from our team, so Sofiia, Magda, and I think Paulina also will help you to find their table. Can you please switch the screen to the HDMI? Możesz zamienić na HDMI, na mój? Ale jestem w... O. Nie ten. Z HDMI, wiesz? To, co przed chwilą było. Pomoglibyście tam? Z mojego laptopa to jest z Tomka, wiesz co? Okay, thanks. Yeah, that's it. Thank you very much. So I'm doing this quantum lottery, so I just wrote a quick Jupyter notebook in this Jupyter Quantum PSNC.pl platform. So if anyone wonders how it looks like this, and it also has the PT series library from Orca installed. It has Qiskit installed, so you can work here if you don't want to install those libraries on your own computer. And also, what is important is if you want to access the Orca Quantum device, which is here in Poznań, this is the way to access it. So if a team wants to use the Orca Quantum computer, we will unlock certain user IDs from the Jupyter platform, and you will be able to send your quantum jobs directly to the Orca system, which is in our other building at PSNC. So this is a way to go. So just find us, the mentors, and we will show you how to do it. And right now I will just start with the lottery. So how it's done? I'm just creating sampling. I'm just sampling a distribution using right now a Orca simulator, but the actual tables will be drawn from an actual Orca device. So this is the distribution and how it looks like. And these are all the possible samples. So right now I want to define a function that just draws a team. And from what I heard, we have 20 tables ready. If there are more teams, then we will have to improvise. But I'm kind of ready to start drawing. So is there a team ready to be drawn? Yeah, okay. So please just remember the number of the table. I hope it works, because it's a live demo to the Orca device. Yeah, so table number 1. You can find it with the girls in the back. So another team. So maybe you in the white shirt. Yeah. Okay. So I'll draw a table for you, and the table number is table 5. Who's next? Maybe you in the blue shirt. Table number 0. So yeah, we're. Yeah, so maybe in the black blouse, or yeah, you. Table number 10. Yeah, okay, so you Adam, I can see it. So for you. Yeah, it's getting longer and longer. Table number 3. Yeah, you in the black, Karol. Yeah, thanks. Table number 2. Yeah, you in the red shirt. Yeah, hi. So for you, it will be Table number 8. So maybe you in the black shirt, yeah? You're together, I don't know, but... Table number 12. Yeah, maybe you guys at the left, on my left, your right. It's taking some time because the most probable samples already have been drawn, but it will be here and eventually. I hope. Yeah, table number 6. Yes. Yeah, you guys maybe on the you're together? Yeah. Okay. Table number 4. I'm just going front to back, so maybe in the white shirt. Table number 7, thanks. Yeah, you in the green shirts? Sorry about, I don't see the names from here, but name tags. Table 11. Yeah, yes, you. Yeah, it's getting longer and longer because the most probable samples have probably been sampled already. So now it's just looking for the least probable samples, but it will find them eventually because we're just sampling the quantum device. Sometimes it takes some time, but... Or it's broken. Oh, no, it's not. Table number 18. Who's next? Yeah, you okay? Yeah. Table number 9. Number 9. This, yeah. And yeah. Just one more minute. Oh, yeah, table number 13. 13. And who is left? You guys at the back? Okay. So. Yeah, it's for you at the back right now. We're waiting. Sometimes it just takes more samples to get to the, because I just cut all the and the probability distribution from the device, but we'll get there, I hope. And in the meantime, I ask you, you are the 3 people left, so do you have a team or? Okay, so may I propose that you form one team or you can also join like other teams because yeah, the minimum amount of people is 2 people, 2 to 5 people, teams. Oh, for you, table number 16, No, both three guys for table number 16, and there are 3 people without a team, so... Okej. To możecie albo zrobić swój team? No to technicznie jesteście. Znaczy,